Okay, so we're just going to be speaking about Cratonic Lithosphere, Metasomatism, and Kimberlites in this lecture. Left this till last because it's by far the most complicated stuff that we're going to talk about. So I'll start off with Mantle Metasomatism because this is a pretty important feature in Cratonic Peridotites, and I think understanding Mantle Metasomatism will also help us understand Kimberlites a little bit. We'll then talk about what Kimberlites are and how they form, and some fairly obvious links to Cratonic mantle. Next, I'll talk about the composition of the Cratonic lithosphere, and finally, a little overview of how Cratonic lithosphere forms and how we can try and deduce what processes were going on. Okay, so I've already mentioned mantle metasomatism a couple of times in the previous lectures. I previously noted that certain compositions, I specifically spoke about rhenium enrichment in PGE patterns, and also mineral assemblages, such as the gabbro vein peridotites that you find in abyssal peridotites, can be modified by the addition or passage of melts. So metasomatism is broadly defined as the chemical alteration of a rock by fluids or melts. There's two main types. One is modal metasomatism, so this is where new minerals are formed, and usually it's fairly obvious that something's been metasomatized. The other is cryptic metasomatism, and these are changes in the mineral or bulk compositions, but you can't really see any new minerals. So this could be something being introduced along the grain boundaries of minerals, or just shifting the compositions of minerals without forming anything new. So a couple of examples here of metasomatism by large degree melts. The first one is one I actually spoke about in the Oceanic Lithosphere lecture, and those are dunite melt channels. So this is incongruent melting or reactive replacement of orthoproxene by olivine. And so this happens because beneath the mid-ocean ridge, basalts are ascending from depth where orthoproxene is more stable, and when they get closer to the surface, they're actually undersaturated in orthoproxene, and they begin to melt orthoproxene, and it forces crystallization of olivine. So this is just a picture from the Omanophylites, and you can see the dunites in the bottom left are these kind of light bands, and the kind of depleted Harzbergite is the kind of background rock is that dark color. We also might see it at subduction zones. An example we're going to talk about later is silica enrichment in the Capval lithosphere, and I think one of the groups did a presentation on this. Okay, so aside from these like fairly obvious large degree metasomatic reactions, which are generally along plate boundaries, we'll also see metasomatism by small degree mantle melts. So these are generally carbonate or CO2 and water-rich melts. We know these are important volatiles in the mantle because we see them if we go and look at volcanoes erupting. It's a bunch of CO2 and water outgassing with the eruption. And you can also see them as either carbonate minerals or hydrous minerals. I've just shown an example at the top here, and these are polymineralic inclusions in diopside. So that's a mantle clinopyroxene. And inside these inclusions, they're actually dominantly calcite, a little bit of olivine, a little bit of serpentine, a little bit of phlogopite. So the reason that this might be quite an important metasomatic agent is that carbonated peridotite can melt at a very great depth, up to about 180 kilometers depth, and even deeper if there's water present. So these volatiles are probably being continuously introduced into the mantle at subduction zones. And then when the mantle upwells, even beneath thick lithosphere, we might be able to get a little bit of melting. And so you can potentially metasomatize mantle peridotites with these very small melt fraction, highly incompatible element enriched melts. And the plot at the bottom is just from Dasgupta et al. 2013, showing the different depths at which dry peridotite, wet peridotite, and carbonated peridotites melt. So I'm just going to go through a few examples of where we might see metasomatism by these kind of melts. The first is the formation of magnesium-rich wurlites. So a wurlite is an olivine and clinopyroxene rock, and you occasionally see them in continental lithosphere. These are thought to form by a reaction something along the lines of orthoproxene plus dolomite, so this is calcium magnesium carbonate, which would be present in your small degree carbonatite melt. And that reacts to form clinopyroxene and olivine and gives off carbon dioxide. So the evidence for this comes from from CPXs, which are highly enriched in incompatible elements. In the bottom left, you can see an example, the Raffone et al. 2009 of whorlite that is formed by this mechanism. And beneath, there's kind of like a schematic diagram from Patco et al., which is sort of showing how this would happen. Just a note that the Patco, the whorlites that they were studying were probably formed by high degree silicate melts, but it's a similar process. So you basically have a melt percolating through your peridotite, you dissolve OPX, and you replace it with CPX to get these big poikilotic looking clinopyroxenes. In the bottom right, you can see that the magnesium-rich whorlites in yellow, these are the ones that are thought to form from carbonate metasomatism, they're really highly enriched in incompatible elements. So we have some evidence for this small degree melt passing through. Got another example here, which is Petite spot volcanism. This is actually a fairly recently discovered type of volcanism. So they're very, very small volcanoes which form just above the axis of where a plate is bending as it enters a subduction zone. So we have some evidence that they're really high in volatiles. They're highly vesicular, even though they're erupting at depths of something like 6,000 meters underwater. They're also highly incompatible element enriched, and they show evidence of isotopic enrichments. And so it's a little, it's not quite certain how these form, but it's something along the lines of that you have these continuous upwelling metasomatic melts, and these create enriched zones or veins in the oceanic lithosphere. And then as this plate begins to bend, as it enters a subduction zone, this causes just a little bit of stretching, a little bit of upwelling, which is either allowing you to remelt these metasomatic veins, or potentially the melting is happening in the asthenosphere and it's passing through these veins and picking them up. And we do actually see xenoliths of metasomatized peridotite in these petite spot lavas. So there's evidence that even this relatively young oceanic lithosphere is getting metasomatized as it moves from a mid-ocean ridge to a subduction zone. Just on the bottom left there is a rare earth element plot where you can see how crazy enriched they are in light rare earth elements. And on the right is a kind of model for how they might form from Pile 2016. And finally, I think Chris might have mentioned this in the kind of Mantle Zoo lectures, but we have the Marid suite, and this is direct evidence of metasomatized continental mantle. So Marid stands for mica, amphibole, rutile, ilmenite, and diopside. These are xenoliths that are pretty commonly found in kimberlites, lamprites, and lamprifiers that erupt through Protonic Lithosphere. They're extremely rich in aluminium, potassium, titanium, and pretty low in magnesium compared to a normal peridotite. And they're highly enriched in incompatible elements like the light rare earth elements, high field strength elements. They have a lot of volatiles, and some of them contain carbonate inclusions. Based on thermobarometry, we can see that these are forming at depths of about 150 to 200 kilometers, so they can be pretty deep. And isotopically, there are two main groups, but they range between so-called depleted marid, which has strontium and neodymium compositions that are more similar to the convecting mantle. And then there's these enriched marids, which seem to be more common, and these are highly isotopically enriched. So these are things that have been metasomatized a long time ago, long enough to develop these isotopic anomalies. So these basically represent enriched metasomatic veins in the Cratonic Lithospheric mantle. Okay, so the main points from that section. Metasomatism is chemical alteration of rocks by melts or fluids, and it can either change the mineral or chemical composition of mantle samples. That's modal or cryptic metasomatism. We see it fairly obviously caused by large degree melts at mid-ocean ridges or subduction zones, but there may also be this kind of ubiquitous global process of small degree melt metasomatism by carbonate and water-rich melts, even beneath thick lithosphere. Kimberlites. Okay, so Kimberlites are very, very complicated. So I've tried to kind of like distill it down to the most important bits and the bits that I'm kind of most sure of. So Kimberlites are these fairly rare volcaniclastic igneous rocks. They also occur as dikes and rarely as lava flows. On the right here, you can see a kind of schematic diagram of like a typical kimberlite. So towards the bottom, you have these hyperbissal kimballites, which are in sills and dikes, and these will tend to be a little bit more coherent and maybe a little easier to understand. They tend to erupt explosively in these pipe-like diatremes. So it's kind of like a carrot shape sticking downwards through the crust. And once you get into the diatreme fascies, this is quite a complex mix of volcaniclastic fragments, bits of wall rock, like even sediments that might get dropped in there. And then at the very top, there's the crater fascies, which is this mix of, pyroclastics and other crap. And sometimes you'll see some like lake sediments if these form a little lake, this kind of thing. So it can be quite, they're quite a mixed rock, quite difficult to understand. So we have a lot of evidence that they are carbonate and water rich. There is some debate about how much of the water in particular originates from the mantle and how much of it is from hydrothermal alteration when they're emplaced. And we can see that in hydrous minerals such as serpentine and some carbonates in the ground mass. In general, they're pretty low in silica and very high in magnesium. And they are full of xenoliths, a mix of mantle and crustal. We'll also see Xenocrysts from the mantle. Some of these might represent disaggregated xenoliths that just fell apart during transport. And we also see some phenocrysts. Now it gets kind of confusing because sometimes the phenocrysts and xenocrysts can look very similar. These have never been observed to erupt because the youngest are about 10,000 years old. If we ignore these Igwisi Hills ones in Tanzania, which are the youngest, then actually I think the youngest are about 30 million years old. So they're, we've never seen one go off. In this section, I'm mainly going to be talking about Kimberlite sensu stricto. This is used to be called Group 1 Kimberlite. There is some confusion that I'll try and address at the end in that the rocks that used to be known as Group 2 Kimberlites are now considered a form of lamproite, and especially in older papers, you'll see these referred to as Kimberlites because they were thought to be the same thing. Now they're generally divided up, and it makes understanding the petrogenesis a little easier. So I'm mainly going to be talking about Group 1 Kimberlite. Okay. So Kimberlites are intimately associated with cratons. In the bottom left here is a map from Gelsma et al. 2008. And they've just put the approximate extent of different cratons on Earth in gray. You can also see the blue to red colors are topography. And you can see that the overwhelming majority of Kimberlites, which are the red diamonds, are found on cratons. And they seem to be particularly associated with the edges of cratons. This might be more a feature of diamond-bearing Kimberlites, which I'll get into, but just something to bear in mind. In the bottom right there is just a map from Priestley and Mackenzie. This is another one of these lithospheric thickness maps. So you can see that in these areas, around these areas where there's sort of 200 kilometer thick lithosphere, we seem to find these clusters of Kimberlites. So they're particularly useful in terms of this course and what we're interested in studying because they act as probes of the Cratonic Lithospheric mantle. So Kimberlites seem to have a very deep origin, at least 200 kilometers depth, and they can carry a huge load of Xenocrysts and xenoliths, and this can be up to 30% by mass of the overall Kimberlite. So they're almost bringing up as much crap with them as the melt itself. Also, because Cratonic mantle is very thick and tends to be very refractory, we don't tend to get many magmas erupting through it. So this is basically our primary source of Cratonic mantle xenoliths and information about the Cratonic mantle. They're also the main source of diamonds. This is primary evidence for how deep Kimberlites form, because you only get diamonds at depths of about more than about 140 to 150 kilometers, depending on the exact temperature. So on the right here is just an example of how we can use xenoliths from a Kimberlite to constrain Cratonic geotherms. And so what they've done here basically is you have a bunch of different xenoliths, you apply thermobarometers to them. I think this would be a mix of clinopyroxene thermobarometry and maybe some garnet thermobarometry. And so for each xenolith, you get a pressure and a temperature. Basically, you can then plot these all up on a pressure versus temperature graph. and you can fit the pressure temperature data using some additional constraints, such as you know what temperature the convecting mantle is, and you know what temperature it is at the surface at 0 degrees, and you put in some sort of estimate of radiogenic heat production. And from this, you can fit that data to find the Cratonic geotherm. Generally, people will take the Cratonic lithospheric thickness as being something around the intersection of the conductive geotherm in the lithosphere with the mantle adiabat. So you can see here the dark black line there that says fit plot. That's the estimate of the Cratonic thickness at this Kimberlite. This is Bultfontein. I'm not sure, that might actually be one of these group 2 Kimberlites, I'm not quite sure. Okay, so when Kimberlites sample Cratonic mantle, it's obviously not a perfect sample. We're getting some sort of partial, possibly random section through the lithospheric mantle that's vertical, because we presume that melts are moving upwards. We don't get a lot of context from this, and obviously we don't get a choice of which sections of the mantle that the Kimberlite sampled. So there's a few problems here. So for example, I will talk about in a bit how certain minerals might be dissolved by the Kimberlite, so then they're obviously not present in our sample. It might not be particularly representative. There's also evidence that certain rock types disaggregate a bit more easily. So I'll talk later about eclogites in Cratonic lithosphere, and it seems like these might be overrepresented in the xenolith samples, because when we look at the Xenocrysts, as I mentioned before, these might be disaggregated xenoliths. There's not actually a lot of evidence of eclogite, not a lot of evidence of a large volume of eclogite in the lithospheric mantle. There's also kind of an interesting question here, is that a lot of the mantle samples that are hosted by Kimberlites are strongly metasomatized. Now, I guess the question would be, is this typical of Cratonic mantle, or are we seeing mantle that's more metasomatized because it is an area that Kimberlites pass through? The seismic evidence suggests that Kimberlite provinces, areas where you do tend to get a lot of Kimberlite eruption, might be a little bit atypical, so we might not be getting a representative sample of the Cratonic mantle. Just in the top right here is a plot from Griffin et al., 2009, and they've done this thing that they describe as chemical tomography, which is where they basically use the compositions of garnets to try and figure out what percentages of the rocks in the lithospheric mantle are Harzbergite, depleted lertzites, or refertilized or metasomatized rocks. Now, this method's not perfect, and it might slightly overestimate the amount of metasomatized compositions, but the point is that there's a lot of metasomatized and refertilized xenoliths in these Kimberlite areas. Below, I've got a plot from Moss et al. 2018, and this is just showing the depths. So again, these are calculated from thermobrometry of clinopyroxene and garnet xenocrysts over time, and these are multiple eruptions that came up in the same Kimberlite pipe. So you can see on the left, in the earliest episode of Kimberlite eruption, most of the xenocrysts were being sampled from a depth of about 120 to maybe 150 kilometers. But over time, this seemed to move deeper. So again, we don't get to pick and choose. We're just getting these random samples of Cratonic lithosphere, and they may not be representative. Okay, so I mentioned before that Kimberlite eruptions are pyroclastic and they're thought to be explosive. So what drives this? We have a lot of evidence that these rapidly ascend through the whole lithosphere. So the primary evidence for this would be the huge Xenocryst and xenolith loads that they have. Obviously, if these were rising slowly, you'd expect these xenoliths to sink down over time, depending slightly on the size and density of the xenoliths. We also see that the xenoliths have minimal re-equilibration. So what I mean by that is that when we do, say, thermobrometry on them, the pressures and temperatures are recording the depths at which these were sitting before the Kimberlite pulled them up, and they're not reflecting like much lower temperatures. We're not seeing any sort of chance for them to react and re-equilibrate at a lower temperature. So basically, this kind of eruption is probably driven by exolved volatiles. These would be water and carbon dioxide. Different people would debate on how much influence each one of those has. And I'm going to talk a little bit about a model from Russell et al. 2012. And this is essentially based on the observation that when you look at xenoliths from these kimberlites, they pretty much always contain OPX, so it's very common. But if you look at the Xenocrysts, these disaggregated xenoliths, we never see OPX Xenocrysts. So this suggests that these are being dissolved. Just in the figure C there, in the sort of top left of the figures, is a thin section image from one of these xenoliths. And in it you can see that there's actually an OPX crystal that's adjacent to a big olivine, and the OPX is being dissolved. You can see that it's indented, and there's this little reaction rim of small grain-sized minerals around it. By contrast, the olivine is not being reacted away, at least as vigorously. So there's a similar reaction to the one I was talking about for forming magnesium whorlites. And so essentially something along the lines of OPX plus carbonates in the melt react to form olivine, more different carbonates in the melt, and exhaust a ton of CO2. So Russell et al. Came up with this model by which you have a carbonate melt to begin with. You start dissolving OPX as it rises through the mantle. Because you're dissolving OPX, you're adding magnesium and silicon, which actually causes the saturation point of CO2 in the melt to fall. So CO2 becomes less happy in the melt, actually drives more CO2 exsolution, which then causes the magma to ascend even more rapidly. You then meet new OPX, dissolve more OPX, and the whole thing goes off like a chain reaction. And they call this assimilation-fueled ascent. Note there's probably a couple of sources of CPX here. One, if you're, couple of sources of CO2 here. The first one is that if the CO2 saturation in the melt is falling as you add silicon magnesium, then you are exsolving CO2 directly from the melt. The other one is that you're actually forming CO2 directly by this reaction. Okay. So it's actually very difficult to establish a primary melt for kimberlites. The reason for this is because they do assimilate so much crust and mantle. And on top of that, they're extremely volatile rich. They're very reactive. They're easily altered once they're sat in the crust. So we don't have any examples of a kimberlite glass, for example. So looking at some of the older estimates of what a primary kimberlite magma might be, you get something in the region of 25 to 31 weight percent MgO, so obviously it's very, very high, and very low silica, so 26 to 30 weight percent. So in the top diagram is, this is a phase diagram from Goodfinson and Presnell, and this is basically showing, as a function of pressure and temperature, what type of melts are present on the solidus. So you can see that at very high depth, so pressures of about 5 GPa or so, so this would be about 150 kilometers. If you start to melt a mantle peridotite, a carbonated peridotite, then the first melt to form is a carbonatite. If you melt it a little bit more, and we're not talking a lot here, just like 1% melting by weight, then you get something that looks like this estimate of a kimberlite composition. So this kind of influenced ideas that these are very deep, small degree melts, or at least agreed with the interpretation. So more recent models will kind of highlight the role of assimilation in forming these kimberlite compositions. So we see in the bottom left here, figure from Giuliani et al. 2020, that there's actually a pretty decent correlation between the magnesium over silicon ratio of a bulk kimberlite and the magnesium over silicon ratio of the peridotites that it contains as xenoliths. So what this implies is that the magnesium silicon ratio in the kimberlite is being strongly controlled by the stuff it's assimilating. So actually a lot of the magnesium and silicon might be coming from assimilation. This means that the primary melt might be something more like a silica-rich carbonatite, so a little bit lower in silica, maybe a little bit lower in magnesium than those initial estimates. And this is pretty consistent with carbonate inclusions that we find in Xenocrysts and megacrysts, which just means big crystals in these kimberlites. So just a repeat of the figure before in the bottom right there, this is a mainly calcite inclusion in a diopside that was brought up in a kimberlite. So where do kimberlites come from? I already mentioned that the presence of xenocrystic diamonds means that these are probably forming at depths over 150 kilometers. Looking at the geochemistry and isotopic characteristics, they have some similarities to ocean island basalts. An important thing to note here is that even though they're very enriched in incompatible elements, they're not particularly rich in potassium. The only exception here are kimberlites that have demonstrably assimilated a lot of continental crust. In terms of isotopes, if you look at low osmium kimberlites, they have isotopic compositions that are kind of similar to ocean island basalts, whereas high osmium kimberlites have osmium isotopes that look a lot more like the Cratonic mantle that they assimilate. So the implication here would be that the melt starts off with not much osmium. If you assimilate a lot of Cratonic mantle, which has a ton of osmium in it, then that ends up swamping the osmium isotopes, and you just see a signature of Cratonic mantle. But if you get one that's relatively pristine and didn't assimilate so much, then its osmium isotopes might be more reflecting its source, and that kind of looks like an oib. In terms of hafnium, neodymium, and strontium isotopes, in the top figure there, they pretty much overlap oib. And so this altogether has kind of contributed to the idea that they have an asthenospheric source, so they're actually forming beneath the lithosphere. There's also some evidence from diamond inclusions, and the majority of diamonds we find in kimberlites seem to come from the lithosphere, so depths of less than a couple of 100 kilometers or so. But there are some certain kimberlites and have a small proportion of diamonds that have inclusions that either come from the mantle transition zone or even the lower mantle. So we're talking depths of like 600 kilometers, maybe even deeper than that. And the picture I've got here from Pearson et al. 2014 is a diamond which actually included, has an inclusion of ringwoodite. Ringwoodite is the high pressure polymorph of olivine. It's only stable at depths, I think, greater than about 510 to about 670 kilometers depth. It cannot form at lower pressures. And so not only is that telling you that this diamond has come from that depth, but the fact that it was still ringwoodite and it hadn't reverted to olivine means that it probably had to come up pretty quickly, because otherwise, if it came up slowly, just through mantle convection, then this diamond would plastically deform, basically relax the pressure on this crystal, and it should revert to olivine. So the fact that it got up the fact that it's still there implies that it got up quite quickly and was kind of frozen in at low temperatures in the surface very, very fast. So at least some kimberlites seem to have these like ultra deep sources, and they might be the deepest melts that we have on Earth. I mentioned before there's a potential confusion with the group 2 kimberlites. So these are now known as a form of olivine lamprorite, or recently been proposed they should be referred to as carbonated olivine lamprorites. You'll see these a lot when you read about kimberlite literature, because they were formerly known as group 2 kimberlites, micaceous kimberlites, and then more recently orangites, which was named after Orange Free State in South Africa, where they were first found. So they have a lot of similarities to kimberlites. They're also carbonate-rich and water-rich, and they have a very similar eruption style. They form these diatremes and apparently explosive eruptions to the true Group 1 kimberlites. There's a few notable differences. You might have spotted these on some of the plots I put up earlier. So in the top one here, it's they're listed as orangites, and you can see the little orange square symbols. They actually have much more negative epsilon hafnium and epsilon neodymium values than Group 1 kimberlites. So this kind of implies that they've been in enriched sources for a long period of time before they erupted. They also have a lot higher potassium, a little bit higher silicon, and sometimes even more extreme incompatible element enrichment than true kimberlites. They're full of phlogopite, which is the magnesium-rich form of biotite, and this is why they're called micaceous kimberlites. So essentially all of these different factors have been interpreted to show that these are melts of metasomatized lithospheric mantle. So the idea here is that you have volatile rich melts percolating upwards and freezing the lithosphere, forming a metasomatized layer. And then at some later date, maybe you get a bit of heat input from a plume, maybe a little bit of rifting or something to allow it to melt. And this will then remelt and form a carbonated olivine lamprorite. It's recently been suggested that they might have a source in the Marid suite. So this is mainly based on the fact that you get an overlap between the enriched Marid compositions and these olivine lamprites, or in this diagram they're also listed as orangites. And it's also supported by little carbonate inclusions in some of these married sweet xenoliths. Okay, so just to sum up, kimberlites are rare, volatile-rich volcanic rocks which are closely associated with cratons. They're our main source of Cratonic Lithospheric mantle samples and diamonds. The primary melts and sources are quite difficult to understand because of the huge amounts of crust and mantle that they entrain and assimilate on the way up, but they appear to form from carbonatite-like primary melts sourced in the ascent. Next, I'll talk a bit about the composition of the Cratonic lithosphere, and then we'll save the models and understanding it for afterwards. Okay, so I'll just start by recapping what I said before in the previous lectures. So Protonic Lithosphere is dehydrated, highly depleted mantle. It's generally found beneath Archean age crust. There might be some found beneath the Proterozoic age crust as well. It's thicker than most younger continental lithosphere, the exception potentially being these these continent-continent collisional belts. And because it's thick, we have a thicker conductive layer and we have colder geotherms, so we have a colder temperature at a given depth. It's more depleted than most of a lithosphere, and so this means that it's generally low density and should be buoyant. It's also very old, so we have ages up to about 3.5 billion years old, which gives us a lot of time for metasomatism or modification of the original compositions. All right. So Cratonic peridotites are commonly Garnet peridotites, which generally indicates that they form at greater depths. We also see some Spinel Prototypes, which would be from shallow depths. Texturally, you can divide these into coarse, or sometimes known as granular peridotites. And these are shown in the top two pictures here from Ionov et al. 2010. So the one on the top left is a granular Spinel Prototype. You can see olivines, which would be I think the largely clear grains. There's some pyroxenes in there, and in the darker blobs are Spinel, sort of an aluminium chromium Spinel. In the top right, there's a granular Garnet Prototype, and obviously this has lots of nice pink garnet in there. The other type are these Pyroclastic or sheared peridotites. And so an example of this is in the bottom right corner. They also get transitional ones between the two. So there's one in the bottom left, there is a transitional Garnet prototype. So these have to have been deformed shortly before Kimberlite eruption brought them up to the surface, because otherwise they're still at pretty high temperatures, around 1,000 degrees, maybe even hotter, and these would re-equilibrate to a coarse texture relatively quickly. In general, the granular peridotites tend to be a bit shallower. It's not always the case, but they tend to have equilibration temperatures below 1,100 degrees C. And so, again, plotting it on one of these geotherms, this will be in the shallow part of the mantle. Picture in the top right is from Ionov et al. 2010. It's from the Siberian Craton, and you can see the granular peridotites are in blue. They tend to be at pressures below, say, 5 gigapascals, 150 kilometers more or less, and below 1,000 degrees C. Sheared peridotites often have higher equilibration temperatures, something between 1,100 and 1,500 degrees C, and this implies that they formed at greater depths. Looking back at the Ionov picture, the sheared peridotites are in red, and these are found at depths of, say, 5 to 7 gigapascals, or about 150 to 210 kilometers depth, and temperatures around 1,300 degrees C. As I mentioned, it's not always the case. There's the figure below is from Katayama et al., and that's from the Katval Craton. And here you can see the sheared peridotites, which are the diamond symbols, and the granular peridotites in the square symbols overlap quite closely. So the way this is usually interpreted, the fact that you get sheared near the base and granular further up, is that you might have more deformation near the base of the lithosphere. Some people might interpret the sheared ones to be stenospheric peridotites, but in general these are being deformed by mantle convection or motions near the base of the lithosphere. However, it might be facilitated by, or even just associated with, it might be easier to deform a metasomatized peridotite. So In the Katayama paper, where they find these two types of prototypes from different depths, they did note that there was actually a geochemical difference between the two, and the shared ones seemed to be more metasomatized. So in this case, it could just be that the metasomatized stuff deforms more easily, or it could be that there is deformation associated with the metasomatism right before a kimberlite eruption. Other lithologies that we find in the cratons include eclogites. This is usually used in sensu lato, like the loose sense, in that people will generally describe anything with garnet and CPX as an eclogite. Strictly, it has to be omphacitic CPX. This is clinopyroxene that is got a significant jadeite component, I think, so sodium and aluminium. But yeah, generally anything that's a clinopyroxene and garnet rock will be described as an eclogite, even if the clinopyroxenes are dioxides. These are present as xenoliths and xenocrysts in most kimberlites, but as I mentioned before, they probably don't represent a huge proportion of the lithosphere, and estimates based on xenocryst studies suggest that it's only about 1%. These are generally interpreted as either chunks of recycled oceanic crust, so this would be some crust that gets subducted and either directly incorporated into cratonic mantle, or it circulates the asthenosphere for a while and eventually ends up getting stuck in a craton for whatever reason. The alternative interpretation is that these are deep mafic melts that come upwards into the lithosphere but don't make it out. They basically get trapped and they freeze, form cumulates or potentially reaction products. So the evidence for a shallow origin is mainly based on oxygen isotopes, which can, so if we have mantle oxygen isotope value of plus 5.5, then anything that is significantly above or below that probably has to have interacted with water closer to the surface. So if you think, I'm not sure if you studied oxygen isotopes in oceanic crust. Anyone? No, probably not. So in general, in the oceanic crust, the basalts near the surface, which are affected by low temperature seawater alteration, get a positive delta 18O signature, and so higher than mantle values. And the gabbros deeper in the oceanic crust, because the alteration is happening at higher temperatures, they actually get oxygen isotope values that are slightly lower than the mantle value. So what we see in these eclogites is the delta 18O ranges from about 2 per mil to 12 per mil, which is a significant range around the mantle value of 5.5. And so that's usually interpreted as them being these oceanic slabs that were incorporated into the craton in some way, shape, or form, have to have interacted with something near the surface. The other way we can do this is europium and strontium anomalies, and this tells you that plagioclase fractionation has occurred. It's a little bit contested, but in general, obviously this plagioclase fractionation can't happen at the depths that we find them now because there's no plagioclase. It's all garnet and CPX. So in the bottom right, there's a plot from Albach et al. 2016, and you can see that Cratonic eclogites generally kind of form these diverging trends. One has an increasing europium anomaly, so that's on the x-axis, at low heavy rare earth element contents. And so these are interpreted to represent gabbros from deeper in the oceanic crust. The other trend is towards very high heavy rare earth element concentrations with no or a slightly negative europium anomaly. And so these are these basically fall along morb compositions where they may have fractionated plagioclase, and they obviously have a lot more incompatible elements than the residues, than the deep crustal cumulates. And in the top right of that plot, you can just see rare earth element patterns from, these are just from crustal cumulates in the Omano, if you like. So generally, these are interpreted as shallow origins. There is a little bit of debate about this. Not everyone's happy with that. On top of eclogites, we also see pyroxenites. These could be hybrids between eclogite and peridotite. And then, of course, the marid sweet veins and other metasomites that I mentioned briefly before. I'm going to spend most of the time focusing on the Cratonic Peridotites because this is kind of where the crux of the arguments about Cratonic lithosphere formation tend to fall. Previously, we noted that it's very, very depleted. So we see extremely depleted PGE patterns, tend to have higher olivine Mg numbers, and low aluminium and calcium contents. Early studies of Cratonic Peridotites, and kind of the first one to note this was Boyd, 1989, noted that Cratonic mantle lies off the oceanic trend. So this is the same oceanic trend talked about in the last lecture, where we have an increasing modal olivine percent as the Mg number of olivine goes up. And this is just, this is easily explained by low pressure mantle depletion. Now, the Cat Valve craton falls off this trend in that it has very, very high Mg number olivine, but has a significantly lower modal olivine percentage than similarly depleted oceanic peridotites. So at first, this was thought to be a primary feature. With a bit more research around other cratons, it actually turns out that Cat Valve is kind of unusual in this way. It's particularly rich in orthoperoxine and lower in olivine compared to other cratons. Some cratons, such as the North Atlantic craton, which is exposed in Greenland, as well as a little bit in Canada and northern Scotland, actually have these peridotite xenoliths that are basically pure olivine dunites. And most Cratonic mantle lies somewhere between Cat Valve, the extremely OPX, like silica-enriched compositions, and these extremely OPX poor Greenland dunites. This led to the suggestion that Cratonic mantle was even more depleted to begin with. So this is the idea from Bernstein et al., 2007. And when they looked at Cratonic peridotites from a number of different cratons, they found that global Cratonic peridotites have an Mg number that pretty much always averages 92.8 for a number of different cratons. So you can see their version of the same plot in the top right, modal olivine percentage against Mg number in olivine. And you can see that the Cratonic peridotites, which are all the symbols on that plot, form this kind of horizontal array that clusters around olivine magnesium number 92.8, but has a strongly varying modal olivine percentage. So this 92.8 is important because this is about the composition of olivine that you'd expect to get when you melt the mantle by about 40%, or when you melt it to the point that OPX is completely gone. So essentially, they argue that all of these peridotites were formed by melting just to leave a monomineralic, just pure olivine residue. So once you hit that point, it's actually a lot harder to melt any further because pure olivine has a much, much higher melting temperature than olivine and OPX mixtures. So basically, regardless of how hot things were, melts, get rid of all the OPX, CPX, most of the garnet, and you're left with pure olivine, and then melting is essentially shut off. So they're basically arguing that potentially all of the OPX that we see in Cratonic mantle was added later by metasomatism, and by the implication is that all of the garnet and CPX as well would have been added back in. This might be mostly true. We do actually see quite a broad range of Mg numbers in Cratonic peridotites. In the bottom is a plot from Pearson and Wittig, 2014. And particularly in certain cratons like the Slave Craton up in northern Canada, you can see that there's a secondary peak in the olivine Mg number distribution. And this one might also have some sort of petrogenetic importance because it's about the degree of melting you'd expect to exhaust CPX. And again, when you remove CPX, it's harder to melt a olivine and OPX mixture than it is to melt an olivine, OPX, and CPX mixture. So potentially we're seeing these peaks in olivine Mg number that correspond to these sort of discontinuities in how easy it is to melt a rock. There's also some olivine Mg numbers that extend to significantly lower Mg number. You can see in the bottom plot that there's a few falling around sort of 88, 89. These could represent melt channels, similar to the dunite channels that we talked about in the Amanophyllite. Some sort of reaction with a melt, or potentially cumulates from melts that intruded and basically got stuck in the lithosphere. So with this, this interpretation leads you to think that a lot of the minerals, aside from olivine, in the lithospheric mantle might actually be metasomatic. And I think based on subsequent studies and kind of work on this over a number of years, people have come to the conclusion that most CPX that we see in Cratonic mantle peridotites is metasomatic, and probably a fair bit of the garnet as well. So in terms of CPX, we have a number of lines of evidence that these are metasomatic. Some of the major element compositions indicate that they're formed from carbonatites, this kind of like willetization process I talked about earlier. They tend to have enriched rare earth element patterns, which are not consistent with them being depleted mantle residues, and they can be quite isotopically enriched. In some cases, they're not in textural and chemical equilibrium with the other minerals in the rock. So in the top picture there, you can see from Boyd's et al. 1997, there's an OPX next to an olivine, and basically along the grain boundary in between the two, CPX has been introduced, and it's reacting and replacing the OPX. So this was probably just due to kimberlite infiltration, like right before this was erupted to the surface, or during the eruption. In terms of garnet, some of the rare earth element and trace element patterns indicate that these are like new metasomatic garnets or potentially alteration of existing garnets. Looking at the hafnium and neodymium isotopes, you can see that some of these garnets actually require like very, very ancient metasomatism. So they have extremely, extremely negative epsilon neodymium, epsilon hafnium values. And the plot in the bottom from Klein, Ben David, and Pearson, you can see just the epsilon neodymium of some garnets. I think these are from the slave craton as well, plotted as a function of the samarium neodymium ratio. And you can see that some of them have epsilon neodymium in the range of -40 to -60. And some of these basically require that they were metasomatized almost immediately after the slave craton lithosphere formed 3.5 billion years ago. So the big question we have to ask based on this is, because if this CPX is being introduced metasomatically, clinoproxene is rich in calcium, and if some of this garnet is being introduced metasomatically, and obviously garnet's rich in aluminium, can we trust the calcium and aluminium contents of Cratonic Peridotites, or do they all just reflect later processes? In terms of the structure of Cratonic Lithosphere, seems to vary a bit between different cratons. Obviously, sometimes we get lucky and we have a good sample of the entire lithospheric depth range from a kimberlite, and sometimes it's just some of the deep bits and the shallow bits are missing, and vice versa. But it does look like there's a slight reduction of olivine Mg number at depth. This could either be due to low degrees of melt extraction. Let's say you have some upwelling mantle that's melting adiabatically. It'll tend to melt the most nearer the surface, so potentially the deeper bits whenever is depleted. Or this could represent small amounts of metasomatic melt added over billions of years to the base of the lithosphere. Spinel Prototypes, which are the shallowest Cratonic mantle samples, can be extremely depleted. They're not always more depleted than Garnet Prototypes, but in this case in the bottom left, this is a compilation of olivine Mg numbers against the depth that they were sourced at for the Capval craton. You can see that some of the Spinel Prototypes extend up to Mg numbers around 0.96, which is very high. On the right is another one of these chemical tomography profiles from Griffin et al. 2009. And so they've calculated the Mg number of olivine based on garnet compositions. So it's a little bit funky. Essentially, it's probably giving us quite a good representation of the upper parts of the lithosphere, because you can see they've compared it to olivine compositions from xenoliths. But near the base, where this garnet is potentially metasomatically introduced, it might give you like a false impression of what the actual olivine Mg number is. But it does, in general, appear to be some reduction of olivine Mg number at the base of the lithosphere. Okay, so just to sum up, the Cratonic lithosphere is mainly comprised of depleted prototypes, and these can either be granular or sheared depending on whether they were deformed shortly before kimberlite eruption. They tend to be extremely depleted and probably required up to about 40% melt extraction. This may have left only olivine as residue. Some of the OPX and garnet and most of the CPX in some of the OPX and garnet and most of the CPX in Protonic Lithosphere was likely reintroduced by metasomatism. Anyway, so we're going to try and tie it all together and talk about how Protonic Lithosphere formed. Just to revisit the formation models that people generally talk about for Protonic Lithosphere, basically we have high pressure melting, which is inferred to be in a plume, and low pressure melting, which could be a mid-ocean ridge or a subduction zone. I'd say in general, a lot of people who work on Cratonic Peridotites seem to focus on the mid-ocean ridge one, and subduction zones don't seem all that popular from what I could read. And again, for all of these different scenarios, the mantle and the crust formation could be linked, or the mantle could be accreted to the crust later. We'll talk a little bit about what evidence we see for that at the end. Okay, So in terms of evidence for a high pressure origin, going back to this Boyd paper, the suggestion for why Cratonic prototypes might be shifted to higher OPX contents, lower olivine contents compared to oceanic prototypes, was that basically the melting occurred at higher pressure. So OPX is stable to higher degrees of melting at high pressure. So at low pressures, say 2 gigapascals or about 60 kilometers, then OPX is exhausted about 40% melting. At high pressure, it might be stable to more than 50% melt extraction. So in the top image here from Afonso and Schutt, you can see that there's, this is just a plot of, as you increase the melt fraction, what happens to the mineral modes. The filled symbols are for batch melting, the open symbols are for fractional melting. And you can see that at 7 gigapascals, the OPX is only disappearing about 50%. The mineral mode drops to 0. Might also have garnet stable to very, very high degrees of melting in this scenario. The lower plot is what this high pressure melting does to the silica. And you can see that at 2 GPa, the silica starts to fall quite rapidly as you melt. Once you've hit about 20 or 30% melting, the silica's down about 40%, so you're getting close to a pure olivine composition. Orthoperoxene has about 55 weight% silica. Whereas at 7 GPa, the first 30% of melting or so, you're effectively not changing the silica concentration in the residue, so you're keeping OPX there. So potentially high pressure melting could generate the extreme olivine Mg numbers we see by removing iron, but keep us at relatively high silica content, so we could have OPX left in the residue without having to add it back in. However, some Cratonic samples have more than 20% OPX, and these require metasomatic OPX addition. Just going back to the top plot there, you can see that for any degree of melting, even at high pressures, the OPX mineral mode never goes over about 20%. So at least some of the OPX has to be metasomatic. So I guess why not all of it? It's maybe not the strongest evidence. This is one that I quite like. We have evidence that some or maybe a lot of the garnet in the continent in the Protonic Lithosphere actually exolved from high aluminium orthoperoxenes. So on the right-hand side, you can see a picture of an absolutely gorgeous orthoperoxene megacryst. It's quite big. It's longer than 10 centimeters or so. And it's not a pure orthoperoxene. You can see these little stripes, the diagonal and vertical dark stripes in there. And these are actually garnet lamellae. And through doing some detailed structural work, Tomlinson et al. Showed that these garnet lamellae are actually controlled by the OPX structure, and therefore they exolved from the OPX. So if you then kind of combine the compositions, you can measure the composition of the garnet, measure the composition of the OPX, and put them back together, then the original megacryst would have been a very high aluminium orthoperoxene. So looking at the thermobarometry now, the garnet and the OPX equilibrated at relatively low pressures and temperatures, so 4.4 gigapascals, maybe about 130 kilometers or so, and about 975 degrees C. But the reconstructed composition of the original OPX is a high aluminium enstatite, and this is only stable at very high pressures and temperatures. So the implication is that this orthoperoxene formed about 6 gigapascals and 1750 degrees C, so really quite high temperatures. And then after its formation, it moved to lower pressures and cooled, and the garnet slowly exolved out. So there's evidence that this might be quite a widespread thing, and this is some work by Gibson et al. 2017, and they looked at the rare earth element patterns of these exolved garnets, and they actually match garnet compositions that we see in other cratons or in places where you can't see it obviously exolving from the OPX. So at the top is what they call a normal pattern, and so this is normal because for a garnet you'd predict it to be pretty enriched in heavy rare earth elements because they're compatible in garnet, and very depleted in light rare earth elements. So they found these normal patterns in the exolved garnets, and these are very common in Xenocrysts and Kimberlite and Xenoliths from cratons all over the world. The exolved garnets also show these sinusoidal patterns, and so these look like something that was crazy, crazy depleted to begin with. So some heavy rare earth elements, but extremely low middle and light rare earth elements that had a melt added to it. And that brings the middle rare earth elements back up because the light rare earth elements are not very compatible in garnet. So even if you metasomatize it, it tends to remain low. And so you can imagine this sinusoidal pattern as being like depleted and then re-enriched. These are also pretty common in garnets elsewhere. And finally, you see these very depleted compositions where the heavy rare earth elements are, only the heavy rare earth elements are enriched and everything else is very, very low. So the fact that we see these in Xenocrysts and Xenoliths elsewhere means that potentially a lot of the garnet in Protonic Lithosphere might have formed by this OPX exsolution. Exsolution from OPX, the implication being that a lot of the lithosphere might have formed at much higher temperatures and then come shallower and cooled down. Some other evidence comes from the iron contents of Cratonic Peridotites. These plots are basically bulk compositions, and you can see there's various curves for melting at 2 gigapascal, 3, 5, 7, and 10. So for each curve, the more fertile compositions would be on the left, and as you remove melt at that pressure, it would move towards the right, so higher in MgO. At low pressures, the iron concentrations during melting should stay pretty constant or even go up a tiny bit, whereas at high pressures, iron should get increasingly depleted as you continue to melt. So this is using the bulk rock iron as a sort of barometer. So these data from Albach 2012, which is a big compilation review paper, and they argue that some of the lowest iron peridotites require deep melting, and so this would be consistent with a sort of plume origin. There are a couple of problems with this. One is that iron is added metasomatically, so it requires some pretty careful screening to figure out what you think is like a pristine Cratonic peridotite, so you can use the bulk composition. There is a chance that this kind of screening is removing some of the low pressure, like high iron residues. There's also a possibility that if these peridotites to begin with were basically pure olivine and all the OPX was added in later, well, you're adding this OPX presumably by some sort of silica-rich fluid or melt interacting with the dunite to make a Harzbergite. And the problem there is that you might actually be diluting the iron by adding OPX. And so through this metasomatism, you might actually end up with a lower iron content than you had to begin with. So that makes this potentially unreliable. You can also see in the bottom plot that some cratons, the iron contents, even after this screening that Albach did, are definitely more consistent with low pressure melting. So some of the Greenland and North China craton residues cluster up around the 2 or 3 gigapascal melting curves. In terms of evidence for a low pressure origin, a lot of this argument rests on the idea that Archean mantle was probably a lot hotter than today. So some of the more popular petrological thermal models suggest it might have been about 250 degrees hotter. So actually you might not need a plume to create these crazy depleted residues. So on the right, I just repeated this diagram from Untitled, showing the Archean Ocean Ridge, and I've circled, I don't know if you can see it, but at the top of the apex of the melting zone, right underneath the ridge, in a hotter mantle, you might have been generating olivine with FO 93 or so, Mg numbers of 93, and that's similar to that kind of constant depletion level that we saw in the Bernstein paper. So Pearson and Wittig tried to do this, basically using the idea that the Mg number in olivine might be the most robust to measure depletion because things like calcium and aluminium can be affected by later metasomatism. And they plotted the average olivine composition as a function of depth. And in the two diagrams in the background there, they've compared it to what you would expect from different melting scenarios. So you can see for the Capval craton, for example, at the shallow level, the olivine Mg numbers pretty much overlap a hot mid-ocean ridge. And then lower down, they seem to kick out, and it's slightly higher olivine Mg numbers than you'd expect from this kind of hot ridge melting scenario. So this might require something like a bit of plume melting, or this could be stacking of oceanic lithosphere, right? You might have the most depleted stuff at the top, and then if you subduct another slab in and stack that up, then you might get a break in the level of depletion and have very depleted residues again further down. So I don't necessarily think this is conclusive, but there's evidence that maybe you don't need these kind of like hot plume scenarios in the Archean, and they might be generating olivines that are even more Mg rich than we actually see. Some more evidence for low pressure origin. So the aluminium contents overlap modern low pressure melt residues. In the top picture here, you can see it's a compilation of all Cratonic Peridotites, the Cap-Val Craton singled out, Cratonic Peridotites, the North Atlantic Craton singled out, and then a variety of modern oceanic mantle residues. So the thing to note here is obviously the Cap-Val has slightly higher aluminium contents than the North Atlantic Craton, but again, because of metasomatism, there's a potential that all of these cratons started out relatively low aluminium contents, and then metasomatism added it back in. The fact that these are pretty low for some cratons like the North Atlantic, and they overlap modern oceanic melt residues, potentially implies that they were similarly shallow melting. Cratonic peridotites also tend to have very low heavy rare earth element contents, and these probably tell us that garnet was not a stable residual phase, because at high pressures, sort of 7 gigapascals, like you might get in a deep melting hot Archean plume, garnet would be stable to above 60% melting. So the fact that we got low aluminium and low heavy rare earth element contents implies that the melting happened at low pressure. For some of these high pressure models where they infer that basically all the garnet is forming from this really high temperature OPX, this might not be too much of an issue, because maybe these were melted past garnet depletion, and the garnet is metasomatic afterwards. But yeah, this is fairly strong evidence that at least some Cratonic lithosphere forms at low pressures. Finally, make of this one what you will, but I think this probably influenced a lot of people's thinking on it. Some seismic reflection profiles across cratons actually found dipping mantle reflectors beneath the moho. And so I've got a picture here from beneath the Abitibi area of the Superior Craton. And you can see the moho, which is labeled, and then this dipping reflector, which is labeled with an M. And this is often interpreted to be like a relic subducting slab. So subduction was ongoing, and it basically stopped and got frozen in. And so we might be seeing a slice of oceanic lithosphere with the reflector, I guess, representing the oceanic crust. So this would seem to support this kind of stacking of oceanic lithosphere that was one of the low pressure melting models. Not everyone agrees that these reflectors should be interpreted as subducting slabs. They could represent intrusions of mafic melts, shear zones, or even these kind of non-plate tectonic, non-uniformitarian ideas, such as delamination of dense mafic residues from the bottom of the crust without it actually requiring a plate subducting. Just like to address the timing of crust and Cratonic lithospheric mantle formation. So we do have evidence that in some cases the Cratonic lithosphere appears to have formed at the same time as the crust. A couple of examples here. The Cap-Val Craton, the crustal ages go up to about 3.6 billion years old, and the mantle TRD ages go up to about 3.5 billion years old. So that's a pretty good overlap. The big exception here is the areas that are nearby the Bushveld complex. And so this was a huge, it's the biggest ultramafic intrusion on Earth, and it's interpreted to represent a large igneous province. This was emplaced about 2.05 GA. And in Kimberlites from nearby the Bushveld complex, so the Premier Kimberlite, we actually see a 2.1 billion year old age peak in the TRD ages. So again, this is consistent. We have this huge melt injection and kind of melting event at 2.1 billion years old, and the mantle is reflecting that with a similar age peak. This even seems to hold in some places where the crust and mantle structure is quite weird. So in the Siberian Craton, the upper crust is about 2.8 billion years old, and the lower crust, which you can use zircon xenocrysts and xenoliths in Kimberlites, continental crust xenoliths, and analyze the zircons in them, or sometimes zircon xenocrysts in Kimberlites. And we can see that the lower crust there is actually about 1.9 billion years old. So the lower crust is younger than the upper crust. And looking at the TRD ages, just going to turn this on. Looking at the TRD ages, we can actually see similar peaks. So in the crustal spectrum, there's a peak around 3.0 to 3.5 billion years ago, and this shows up in the TRD ages of coarse dunites and olivine megacrysts from included in the kimberlite pipes there. There's a major crust peak about 2.8 billion years old, and we also see a major peak in the TRD ages here. And finally, the lower crustal ages are about 1.9 billion years old, and there's another peak in the ages of Spinel Prototypes there. So at least in these examples, the crust and mantle appears to have formed at the same time, even where you have complicated, multiple crust forming events. Sometimes it doesn't seem to match up at all. So here's an example from the North Atlantic Craton. There's some Spinel Prototypes with TRD ages, which go all the way up to 3.8 billion years old. The crustal age is a little uncertain because it's buried under tertiary basalts from the North Atlantic Igneous Province. But the crustal age is either about 2.7 to 3 billion years, or it's Neo-Archean, or it's Paleoproterozoic, about 1.7 to 2 billion years old. So there, the mantle appears to be older than the oldest crust in the region. The picture here is a compilation from the Sass Craton, and the Sass Craton is a little Cratonic kind of microcontinent or relic. They got caught up in the Trans-Hudson orogeny. And the Trans-Hudson orogeny would have been like a kind of Himalayan scale, absolutely enormous mountain building event, which happened about 1.9 billion years ago. It's kind of the end of a Wilson cycle, so a cycle of rifting, which happens about 2.1 to 2.2 billion years ago, and then everything got closed up and smushed up in a huge orogeny. What you see in terms of crustal ages in the Sass Craton is that everything's Archean. So it ranges from about 2.5 to 3.2. The main peaks, younger Neo-Archean, about 2.5, but there are some very old rocks there. But not one of the TRD ages analyzed from the Sass Craton comes out older than 2.5 billion years old. The peak in TRD ages, which is here, actually reflects rifting and the rifting and collisional cycle in the Trans-Hudson orogeny between 2.2 and 1.9 billion years ago. Okay, so I can't really give you like a satisfying conclusion here. As far as I can see, the way that Cratonic mantle forms is a bit of a mess. So there are fairly convincing lines of evidence for both the high pressure and low pressure formation models. I think there's potentially a bit of variation between the different cratons. I'd say a lot of the high pressure evidence seems to come from the Capval. So maybe that incorporated a greater proportion of high pressure lithosphere, or maybe people who work there are just more conditioned to seeing things in a high pressure lens. Cratonic lithosphere may be the same age as the crust it's associated with. It sometimes incorporates older chunks of previously depleted mantle, which might be similar to what we were seeing with the New Zealand and the oceanic peridotite examples, where you have these older chunks being incorporated as the lithosphere forms, or in some cases it's significantly younger than the overlying crust. So I think the times that you do see the age differences probably tell us that lateral accretion or movement of crust relative to the mantle beneath it, potentially during orogenic events, or just from incorporating these older chunks circulating in the mantle, is probably important regardless of whether we prefer a high or a low pressure melting model.